Yeah.
So we are going to go over vectors today. Woo!
You're performing arts. Yeah. You're more of a dance kid.
Do it this way.
My mom was a dance kid.
Your mom was a dance kid?
Yeah, well, she was a performer. She's an actress and a teaching artist, but she was better at dance. She was never a triple threat. She was always like, I can't sing, but I can dance and act.
Not triple.
And then I can sing and act, but I can't dance.
Oh.
I can dance like I have good rhythm. I'm not good at the instructions.
You're just not going to do that.
I'm not good at the instructions.
What's up?
I mean the test.
The test?
Chapter test.
Oh, God. You got like 6 minutes.
Yeah.
Why are you leaving? 10. Chapter 6 test.
Chapter 6 test.
Look at this beautiful
6-1, 6-3. We never took a test yet?
The might have been on a grade.
This is chapter 6 right now. Starting chapter 6, right, Maggie?
Yeah.
This is 6-1 notes, right?
Yes, it is.
Thank you.
Okay. There's chapter 6 test. There's like.
I'm pretty sure it's like some competition now. It could be that.
Perfect.
Yeah, you're the worst one.
How about chapter 5? 5.
I don't care.
You said
But you can write it somewhere else.
Right.
I had to shoot it.
I did the check. One for you, so you gonna put your name on this one?
It's under my phone.
We got it. It's just paper. Okay. So, this is
Oh, I forgot to do Mountain Dew.
There you go. Oh, look at a blue pen and everything. Perfect. Enjoy. All right, back to the beginning here. Hopefully you fast forwarded that, Danny, if you're listening.
Yeah, Danny.
I got a lot of this.
Mm-hmm. See, this is going to be called Vectors in the Plane. Mm-hmm. Which, if you remember back to last year, or Algebra 2 curriculums, you probably got introduced to some of this. I hope. Let's try this again. Because I just taught it the other day, so you should probably...
Pretty umbrellas.
Aha! There it is.
Whoa, vectors in the plane.
Here they are. Okay. So, woohoo! Vectors are basically just rays. So there you go for that.
They're arrows.
Yeah, they're lines with a arrow. Yes. They have direction and magnitude. Yes, they do.
Ooh.
I know, huh?
It.
Oh, good. All right, let's zoom out a little bit. Mm-hmm. There they are. All right. Boop. There. So, two-dimensional vectors, because we're going to do it on a grid. An ordered pair of real numbers that represents a direction or a directed distance is a two-dimensional vector. So what happens is you might be given this coordinate and this coordinate, and it will say that this is the initial point and this is the ending point, and then you can make a ray from it. So it is different than a ray because it actually has a length. A ray goes on forever, but a vector actually stops at the coordinate. So, two or more vectors whose sum is a given vector are called components. So you can add components together, put a ray with another ray and make a super ray. All right. And then a standard representation of a vector is an arrow from the origin to a point AB. You can actually draw a vector anywhere, like this one down here, on the grid. However, to help ourselves out, a lot of times we just do it 0, 0 to the coordinate that they give you. The component form of a vector uses the angle bracket notation, and you probably can't decipher that from this tiny text here, but it turns out that it's like a less than and greater than sign, but not quite stretched out. So that is your component form, and that will be the one where you're going to continue to ask me, wait, what does that mean again? So component form means not as a regular coordinate. Yeah.
Okay, is it still like the XY?
Yes. Mm-hmm. It'll be horizontal movement and vertical.
What does that mean? Does that just mean it's a vector?
Yes.
Okay.
Yeah. All right. And again, it says the horizontal and vertical components versus the actual coordinate itself. Because it doesn't necessarily start at the origin, which is what I was saying earlier. So U and V are, it turns out, the same vector going in the same direction, same length, all of that stuff. And in fact, they're parallel. We'll talk about that in a little bit. But they have the same horizontal and vertical component. The placement does not matter.
So are we going back to like slope formula and then figuring out 2 points to make the slope formula?
No, because slope is not what we're going to talk about. We're going to talk about the direction angle.
Oh.
So we won't talk about rise and run. We'll talk about the angle of right here. Yeah. Mm-hmm. Very exciting. Yeah. All right. So let's see if I can scroll now. All right. So turns out that you can do what they call the head minus tail rule. I am now remembering that I have some notes on this for a formula sheet. So anyway, head minus tail rule means that you can go ahead and put two vectors together. So an arrow with an initial point of x1 and y1 and a terminal point of x2 and y2 tells you that you can basically just do the slope and get there. Right? Because in slope you would have done y2 minus y1 and x2 minus x1 to get it.
This just represents, what does this represent? Like, is this representing both vectors or just one?
Well, right now there's no value, so yes, it represents both of them. Yeah. All right, so if we go ahead and do the example here, which says use the head minus tail rule to prove that u and v are the same vector, we would find the two coordinates of each of them, the initial point and the terminal point, and then we would put them into this formula and realize that they're both going to have the same component form. And because they have the same component form, they are the same vector, just placed different. So this coordinate over here is negative 5, 1. This one is negative 1, 3. Over here, 0, 0, yay. And 4, 2. So if we have all those coordinates and we take our x's and subtract them and our y's and subtract them, we're going to get the same coordinates. So vector u, they like to use u and v a lot in vectors, is going to come from, oops, the x's subtracting, so 3 minus 1, and the y's subtracting, negative 1 plus 5. And the v vector is going to come from 2 minus 0. Oh wait, sorry, we're doing x's first. Oh, I did it like slow. Sorry. 3 minus 1 and negative 1 plus 5. There we go. 4 minus 0. Thank you for your understanding. All right. So turns out that both of those become 4, 2. And so because they're both the same component form, they are in fact congruent vectors, same vectors. Yay! So there you go. But of course you could just say they have the same slope, but you'd have to know where it ends. So.
And they're asking for you to use the head minus tail rule.
Right. Yeah. Mm-hmm. So, magnitude. If v is the arrow from that point to that point, then the magnitude of v, which we like to do with absolute value signs, but that does not mean that we are actually doing the absolute value. Okay, so you gotta watch out for that. Also, as you're looking at this, perhaps you've noticed that the letters U and V, when they are mentioning them, are bolded. And that is because we don't want to compare them to when we were doing triangles before, and we said that capital A is the coordinate and lowercase a is a side length. We don't want to say that A is a side length or V or U are side lengths. If I made this a bolded A, then that would actually mean it was a vector on the other side. So, those are bolded on purpose. All right. If you do not want to do bold because you're writing in pencil, you can also put the actual vector symbol on top, which is like array, but only half of the arrow. So, alrighty. So, turns out that the magnitude is literally just, do we recognize this formula?
What is it? It does. I do recognize it. And I don't know.
It's just the distance formula. I know. So really, the magnitude is actually the length of the hypotenuse. Because you can turn every hypotenuse. I just made a shorter word. Okay. Because you can make every single vector into a right triangle. And so officially, that hypotenuse is the magnitude. Or you can think of it as a line, but I like to make them into triangles. Same thing happens here. If you actually know the component form, you can just take the x value and square it, and the y value and square it, and square root it, because they've already done the difference if it's in component form. So, we also have something called the zero vector. So, imagining putting a vector on one point. It is possible, yeah.
How are we using x and y and v? What does that A and B mean when it's if v is this then?
It's because they changed x and y in vector format to be an A and a B so that you don't think that it's just a coordinate.
Okay.
So basically A equals x and B equals y. But they like to call it horizontal movement and vertical movement. All right. So the zero vector, having those components on the side there, the component form, has neither length or direction. So, sorry. All right. So what is the magnitude of U up here?
What is my magnitude?
Well, we already did all the subtraction and got 4 and 2. So really we can just skip to this part, which says that the magnitude of the vector is just 4 squared plus 2 squared, square rooted. So magnitude of U. Let's do U. So the magnitude of U is 4 squared plus 2 squared, square rooted. So 16 plus 4.
Doesn't that mean that the magnitude of u and the magnitude of v are always the same?
Yes. Mm-hmm. So square root of 20 or 2 square root of 5 if you want to put it in the lowest rational form or whatever, but yay, ultimate answer. Okay. But square root of 20 is fine. I would not go to the decimal just because it's not exact. It is messy. Mm-hmm. Lex would concur if you were here.
Yes, he would.
All right. Righty. How about scroll on this thing? Yeah? Okay, that sounds better. So, today's unit, like that first unit, so there are a lot of terms involved in this. Just so that we're all kind of caught up on what we should know about vectors. So it turns out that you can take vectors and add them. In fact, that's kind of how we figure out motion and things like that. Because, for instance, we love to talk about a plane flying and then wind blowing and how together they make the plane go actually in a different direction than it was intending. And at a different speed than it was intending. So, if we are given two vectors, we can in fact add them together. There's two ways that you can do this, but pretty much I never use this way. I only ever talk about how you take one of them and put it on the end of the other one, and now you've made a triangle. Not a right triangle, but a triangle that we can use law of sines and cosines on because we might know an angle or something. And in fact, this diagram that the geometry students were working on uses law of sines and cosines. It actually was a vector. All right. So this one is the parallelogram representation because they're assuming that this side is going to be the same angle and measure as this side in a parallelogram, and then the same for this and this. And so the resultant vector is in the middle. But that's just too many vectors all the time. I just don't need to go there. Yeah.
So what's the sum resultant of vectors? Like what is U1 and V1 mean? Like,
those are the coordinates of the U vector.
The first coordinate is the 1 and the second coordinate is 2.
Yeah, but the component form of it. They're saying that the vector in component form, so it's horizontal movement and its vertical movement, are U1 and U2. Yes, this is after you already had them act as coordinates. So now you have it as a.
Would be going to be the same if you put it there?
Yeah, I think we're talking about a new U and V now.
Okay,
Yeah. It's kind of like every time we talk about X and then we keep changing it. This time U and V are changing.
So is this like, are those U's like A and B's?
Yes.
But wasn't it like U and V before?
Yeah. They're common letters in vectors, V and U.
But how can there be two U's and two V's? I thought it was supposed to be
One is V1, one is V2.
Yeah, one is the horizontal direction and one of them is the vertical direction of the U.
2 points, not 1 point.
Okay.
All right. So we take the horizontal movement of vector U and add it to the horizontal movement of vector V, and then the vertical movement of the U vector and the vertical movement of the V vector and put them together. And now we have the component form of the resultant vector, which can help. All right. Then we have a scalar, which is just a fancy word for a number that you're going to scale something. Okay? So that's kind of why I call it a scalar, because it comes from scale factor, so it's a scale. I suppose you could say scalar. Anyway, done. A real number that gets multiplied by a vector. So you can take every vector and make it bigger than it already is by just multiplying by a number. All right. And remember that multiplying is the same as dividing. You just would be multiplying by a fraction. So you can make something smaller, like this one here, multiplying by a half. It made it smaller, or half the size. This one was multiplied by 2, and so it made it twice as big. But this one was multiplied by -2, and so notice that it has an arrow actually going down versus up. Because if you multiply by a negative, you are now changing your values to be going down and to the left instead of up and to the right. So all it's saying is take that k and distribute it. Alrighty. Woohoo, vector operations. Okay. Alrighty. Then we have something called a unit vector, which will make it kind of exist on our unit circle. Because we are talking about a vector with a length of 1, just like the radius of the unit circle. So we are forcing every vector to have a magnitude or a hypotenuse of 1. And so in order to do that, you have to divide every thing by the magnitude. The vector components by the magnitude, yeah. So basically like in the next one, or in the previous one, we are saying that that's our scalar or our multiplier. So you're going to do 1 over the magnitude. And that 1 over the magnitude is being distributed into both pieces of the component form. And now you have a unit vector, which we will do an example of so that I don't have to have so many words. You will get sometimes this phrase, because remember that there is a 0 vector, a vector that's like a single point. So they will try to tell you things like, well, remember how we can't divide by 0, so make sure that the vector is not the 0 vector. Okay. It's kind of like if you talk to Henry and he talks about how I make up triangles that have side lengths of 0, but
Yeah.
that's because it's fine. Okay, use your imagination. All right, so we're going to find a unit vector in the direction of this component form, -1, 4. So all it says is to find the magnitude. Remember that if it's in component form, the magnitude, which we're going to denote because this is, oh, we don't know what this one is. All right, I'm just going to write magnitude then. So the magnitude is going to equal the square root of -1 squared plus 4 squared. Or the distance of a triangle with a side length of 1 and 4. All right. So that means that 1 squared plus 16 because of 4 squared. Oops. Which is the square root of 17. So gross, but we'll make a nice side length of 1 if we take this number and multiply it as a scalar to -1 and 4. We are now going to have a unit vector. Meaning if we then did the same exact thing to the new vector that we're getting, we would get 1, because that's the whole point. So that means that the ugly vector is -1 over square root of 17 and 4 over square root of 17. And that's it.
You would come, oh, because they're pointing.
So, where am I getting all this from?
Like, what are you using to get that? Like,
You're using the scalar. No. Yeah. Because you gotta find the magnitude.
Do you mean the square root of 17 or
No,
the
I'm
boxed
thinking-
answer?
both. So do you use the A and B for the square root one?
Yep, so this is A and this is B and this.
And then what about the box? Why is there 4 and a -1 above?
Because the original problem had a -1 and a 4, and so we just took those pieces and divided by the magnitude so that we could make a unit vector.
Okay.
So if I now do this process to these numbers, I'm going to get 1, because that was the hope, to get 1 back out. But I'm not going to, because no thanks. All right. Yeah. All right. So, another thing is that there are something called standard unit vectors. So instead of using component form, they use a vertical shift and a horizontal shift. So I ends up being your horizontal movement, and J ends up being your vertical movement. And so they're saying that if you follow this vector and this vector, you will get to the resultant vector. So I is your horizontal movement, J is your vertical movement. It's kind of like just saying that you'd put like an I here and a J here and a plus sign. So anytime that you are changing from one vector to the next, all you need to do is put an I next to the A value and a j next to the b value, and now you have your unit vector, standard unit vector. Yep, that's what we did. So as we have up here, the component form, -1, 4, in those fancy brackets, can actually be -1i plus 4j in the standard unit form.
Would it be minus 4j if it was -4?
Yes. And don't pretend that this I is like -1, square root of -1, because it's not.
Okay.
Totally different I. Notice it's bolded. So I'm sure that makes a difference in your handwriting. Okay. So, vectors are intense.
Oh my god, how many more?
Too many. Just don't go. Okay, let's go. 1, 2, 3. Okay, 3 more. All right. Allie is fine with 3 more slides. Okay. So here we go. Direction angle of a vector. So this is what I was talking about a little bit earlier. How we are now talking about a ray, but the ray has an angle. So that's why we don't necessarily talk about slope, because we get to insert this angle later. So the angle measure of your vector is going to take the vertical component and the horizontal component as a fraction and take the tangent inverse of it. Because technically this vector has an adjacent side and an opposite side, and so we'd be using tangent to find the angle measure. So without necessarily memorizing the direction angle vector formula, you could just make all of them into a right triangle and use the tangent. But there you go. There's also this piece over here that says that you might, in fact, have to add 180 because you might be in the wrong quadrant. Okay? Because if the vector points towards quadrants 2 or 3, so if it's over here, I am not trying to find this angle measure. Okay, because that would be weird. Instead, I'm going to move it so that it's actually over here. Okay, that's supposed to be a straight line. So I'll draw that better. Because if you add 180 to the existing vector, you're now over here in quadrant 1 or 4, which is where we want it. So if you're ever going negative, like your horizontal movement is negative, you're going to have to add 180 to that. So you'll know because you're trying to get an angle that's more than 90 degrees, and that's not possible with trig, so don't do it. All right. So guess what? We're back to -1, 4, and we're going to try to find the direction angle of that vector. So technically, they want you to take the tangent inverse of y, which is 4, over x, which is -1. Because that's like your x component and your y component. So you could also say that this is b and a, like it was in the previous example. Yeah. So, let's see what it does. Hopefully you're in degree mode, and 4 divided by -1. All right, so we officially have an angle measure of -75.96. Which is a little weird to think about. So if we add, well, I don't know that that's gonna, no. So we're over here at -1/4. -1/4. Because -1/4 is technically over here. But this one got us negative because it already did it for us.
But that's in the 2 quadrant, so when you have to plus 180.
Yeah. But if you do, then you get 104.
And
That's not right.
And that's not in quadrant 1, because that's back over there.
No, not if you add 180. You add a positive to a negative, that's going to be different.
It's still going to be positive 104.
Oh, okay.
Hey, what is up with this math?
quadrant to it.
I don't know.
Well, why are we not adding
That's right.
180 if it's in quadrant 2?
Yep.
No, she did, and she got 104, but it still isn't in quadrant form.
So we're gonna answer that in just a second when I go over here.
It's okay, thank you.
Okay. I have it all written out, but let's see. Chapter 6. All right, so the answer is 104.04. Okay. But that's technically not back in quadrant 1 or 4, but they did.
So 104 degrees.
Yeah, 4.04 degrees. Boop.
Do you write 180 and not 108?
I did. I should have just erased the top of that, but I didn't. Okay.
Or was it good?
But 108 would have made it a little bit more palatable, but there you go. That's what my official notes say. Okay. Where are we? Ooh. We're going to do a resolving the vector into components. Oh, okay, this sounds exciting. All right. So we added the 180. It just felt wrong. Okay. That's all I got. It's Friday. It's very exciting. It is going to be 60 degrees on Sunday. I can't take it. That's so exciting.
Working.
Oh my gosh.
But
Outside?
I'm pretty sure, no, inside. It's gonna be, do you know who Rick Steves is? Well, he's a travel, is a travel show. He's gonna be there, and I'm gonna try to ask to get a picture with him.
You mean you don't want his autograph?
No.
That would be like so weird now.
Mr. Rick Steves, Mr. Steves.
Maybe after you take the selfie, he can sign it on the picture.
Sign my phone.
Yeah, but like with the marker that you could, yeah. Well, you could, not on your phone, on the picture. Okay. So, if the vector v has direction angle theta, super, the horizontal and vertical components of v are found using this. So let's say that you wanted to go backwards from what we just did. You were told that this certain vector has a certain angle measure. You can go ahead and use this formula to go backwards to find the side length. You would think that you might be able to do this using some other mathematical whatever, okay? But it turns out that we don't necessarily have like the right triangle formula to do that if we only know one angle, right? If you're going to use trig, you need an angle and a side length. If you're going to use sines and cosines, laws of all of those, you need at least like 3 things going on. So in that case, all you need to do is take that angle that they have and get the magnitude of the vector and multiply it by the cosine of that for your horizontal movement and the sine of that angle for your vertical movement. So if we find the component vector with a direction angle of 240 degrees and a magnitude of 8, we would just plug that in to our formula. So the component form of our vector v is 8 times cosine of 240. And then that's a times. And then our vertical component is 8 times sine of 240. There it is. For some reason, this wasn't paid attention to last year, and so most people just tried to do it by hand. But hey, here's your formula. So, if we do 8 times cosine of 240, we're going to get -4. Oh, that works out nice. And then if we do 8 times sine of 240, we get kind of a gross number. Does it say anything about rounding? No. Yeah. Because I would have loved to just round that to 7, but I didn't.
I don't like
So
rounding.
is that the component?
Yeah, so that is the vector that will make a 204-degree direction angle. Yeah. Yep. Super. Alrighty. Oh my gosh, now we get to do an application. It's gonna be great. All right.
Is that
There's an airplane involved. Okay.
There's what?
An airplane. Yeah.
That's sick. It's planes. Get it?
Oh my gosh,
Planes.
planes. Oh my god, I can't even take it. I feel like I should call you Will, but I'm not going to. Okay.
No, Will's better at it.
True. If you were here, he would have owned that. Right. So, moving on, an airplane is flying in a direction of 15 degrees at 370 miles per hour. Wow. A wind is blowing with the direction, doesn't say, 235 degrees, 2-ish. Okay. At 30 miles per hour. And we need to find the component form of the velocity of the airplane, meaning the result of after it's trying to go at 15 degrees at 370 miles per hour, that it ends up actually having a wind blow it. So let's draw a diagram of this. Alrighty. What is this? Apparently I'm only drawing one. So an airplane is flying with a direction of 15 degrees. So we're going to go here. And it's at 370 miles per hour. Turns out that anytime that they talk about speed, that's velocity or the magnitude. And the magnitude is the hypotenuse. So it kind of goes in this really great circle. So if they say speed, speed is velocity, velocity is magnitude, magnitude is a right triangle's hypotenuse. There you go. So they just want the component form of the velocity of the airplane. It's the next one that wants the whole thing. All right. So we're not going to take into account the wind until the next one. So they just want the component form of this end piece here. So basically they want the opposite and the adjacent side. So we can do that with our basic trig, or we can do that with the formula that we just had. So the formula that we just had said that you could take the magnitude, which we know is the velocity, which is the speed, and multiply it by cosine of 15. And that's the x component. And then we could take 370, which is the magnitude, times the sine. Oops, that's a really bad vector marker. Okay. So if you do those moments, you're going to get 357.4 and 95. Yeah. Ooh, I got 8.
Ooh. Well, 7, 6, and 8, so.
Oh, I heard 6, 6, and I was like,
No.
oh, okay. That's not 8, but okay. 7, yes. Alrighty. So, if we're going to find the actual ground speed and direction of the airplane, we would need to then do this same exact thing for the wind vector. So if we go ahead and just do 30 times for the wind, 235 inside of cosine, and 30 times 235 inside of sine. Oh, that's a 2. Then we can take the wind vector and add it to the airplane vector and have our vector that we can find the direction angle of. So the wind vector becomes a very negative moment of negative 17.2. Wow, something's funny. So that's our wind vector. We're going to add that to our airplane vector, and we'll have the resultant vector. And to add them together, it's literally just adding. Yeah. And 95.8 and 24.6. So So if you add 357 to negative 17.2, you get 340.2 and 71.2. And since we know the component form of the resultant vector, all we need to do is that tangent inverse formula to find the direction. So the angle is tangent inverse of the y value over the x value from the previous formula, which apparently is 11.8 degrees.
What does coordinates mean? It's figuring out where the airplane currently is.
It's finding the direction that it actually is going based on the fact that the wind is happening now. So because the wind is kind of blowing this way, the plane ends up going in a different direction. Actually, it's kind of going this way. So the wind is hitting the plane, and so instead of its original trajectory of 15 degrees at 370, it's now actually going slower at 11.8 degrees.
What's that number at the end? What is that?
11.8 degrees.
Is
So
the degree window it's going at? Oh, okay.
yeah. So yeah, this one. Yeah. So it got scooted. Alrighty. So, we now have an assignment, which apparently I made a note to myself from last year that says that numbers 40 and 43 are a check of example number 6. So I believe they are a check of understanding if you got that one. So, this is our assignment, page 511, which I will erase things around it. Number 2, 3, 7 through 9, 11 through 33, but only the odd ones there, 39 and 40 through 43. So, the answer key is on HeadRush, and then the notes filled in are also on HeadRush, so you can kind of check those out as well with maybe a better handwriting. All right.
Thank you, Becky.
Oh my gosh, you're welcome.